Okay, sorry for the setup. It's maybe I'll ask to change classrooms because this is not this is terrible. Okay. Okay, so should have probably we may change classrooms. I'll send out an announcement. Please follow the emails. And so we did martingales, and now I want to move to define random walks. And so we're going to start generally with Markov chains. And in order to define Markov chains, I want to review very quickly the basics of infinite product spaces. So suppose we have we're going to write G. G is going to be a set, but at some point it's going to become something else. But it's going to be a set. Okay, and we're going to be actually thinking of infinite, but we can think of finite sets. Okay, and but countable, never uncountable in this situation. And we can look at the space of sequences. So what's the space of sequences? Just G to the power n. This is the space of all sequences. I'm write omega 0, omega 1, so on, such that omega j is in G for every j. So this is just infinite product space. And we want to put a measurable structure on this space. We want to define a probability measure on this space. So we first have to put a measurable structure on the space. So in order to define a measurable structure, what you need to think about is, what do I want to be measurable functions? If I have functions to R or something like that, what do I want them to be? Which functions do I want to be measurable? And so what you realize is, so here, functions are going to, if you think about functions into G, then what is measurability? Well, it's just that since I'm talking about a countable set, I'm thinking about something being measurable. If I can ask, is it here? Is it here? Is it there? Is there? Those will generate the sigma algebra. So the singletons will generate the sigma algebra. And so if you think about it a little bit, not too much, then you actually realize that what you need to do is you need to define the cylinder sets. Okay, so what is a cylinder set? So a cylinder set is just specifying finitely many values. So the way we can define it is we can take some omega inside my infinite space here. So this is a sequence. Omega is a sequence. Okay, and then we can take and we can define and we take some number. So let's say n. Okay, and then we can define the cylinder set with respect to omega and n. This is going to be just all the sequences that agree with omega on the first n places. Maybe first n plus 1 spaces because it starts with 0. Okay, so this will just be all the, say, eta in G to the n, such that eta j is equal to omega j for every j between 0 and n. Okay, so this defines a certain subset. And then the cylinder sigma algebra, so this is the cylinder with respect to omega and n. You can see that if I change omega in any place which is not the first n plus 1 places, it will still be the same cylinder set. So this omega is not the unique omega. There are many omegas that will give the same cylinder set. And these sets span or you take the sigma algebra generated by these sets. Okay, so so we take F be the sigma algebra generated by all of these things. You run over all possible omega and all possible. Okay, so this is the minimal sigma algebra that you have that will contain every single one of these cylinder sets.
This is like taking the Borel.
Well, there's no topology.
If you take the product topology on the discrete.
Yeah, if you take the discrete topology and product topology of that, and then it will be the same thing as the Borel, because these are the things that come from the singletons. Okay. It's important to say that this is not the full sigma algebra. So this will not have every single event in here. This is already too big. Okay. If I were to take a finite product, it's no problem because G is countable. But you should be used to it. Basically, what you say is in measure theory and probability, you always do the naive thing. You don't try to just do general things. So all you're saying is, okay, I want to be able to ask the question, was my sequence, so you can think of a random sequence, right, with values in G, was my sequence at time 5 at position X? That's all I want to say. All right? Now, if you say these are all valid questions, meaning those are all events, those are all measurable subsets, then when you kind of generate the sigma algebra from those, you get all of these objects. Okay, that's what you get.
In probability, we used to talk about like IID, right? Infinite sequences of IID.
Yes.
And we never said why we know that such.
Yes. So yeah. So yeah. In Markov's probability, I kind of sweep that under the carpet.
But this is the.
Does there exist a space? But this is much more than IID. So okay, I'll state the theorem. I'm not going to prove anything. This you should have probably seen this in measure theory, but if not, then you can go over it and understand the probability or measure theory book. Infinite product spaces is something well known. I'm not going to do it, but I'll say a theorem in a minute. Okay, I'll give a theorem. What probability measures can you put on this space? And one of the probability measures is take a probability measure on G and take its infinite product. That's just that's the example of IID. But there are other probability that you can put in. In fact, we'll be interested in others. Okay, it's always when you take the point of view of probability, you always take the point of view of some kind of independence. Okay, when we did martingales, there was some kind of what was the independence? Independence was the conditional expectation is the previous guy, right? That's some form of independence, right? I kind of like the average stays the same or something like that. Here we're also going to see something called the Markov property. The probability measures that we're interested in are going to have the Markov property. So it's some form of independence. Okay, IID is kind of the strongest form of independence. It's like everything is independent. All the coordinates are independent, but that's very, very strong and doesn't give too much, right? But basically, the Finetti's theorem tells you all the possible examples of that. So you have to be careful. I mean, you have to decide what generality you want to work with. So this all makes sense. If G was a finite set, by the way, this would still be open. So I'm just saying infinite here is it's not necessarily that you have to do infinite. Okay. Now I want to put probability measures on this sigma algebra, right? So how do we do it? Well, we just do the finite dimensional objects and kind of work our way up. How do we work our way up? We need the fact that these things are consistent with each other. So yeah. So how should we phrase it? Yeah. 1 second. Let me make an exact statement. Okay, so yeah, so let me say something first about yeah. So let me say something first about processes on this. So if I have such a space, I can define a function from my space, from my probability space to or I can define a function, and let's put a little t here, and define a function xt. It goes from my probability space to G. Okay, and I want this to be a measurable function. Measurable into a discrete space is just means that when I pull back the singletons, I get events. Okay, so and I'm just going to define it. So this guy eats an omega, right? Omega is an infinite sequence and spits out, well, omega t. That's one possible way to define a function. You see, the little t tells me which omega do I spit out. I spit out the t coordinate of omega, and what is this? Well, it's basically just looking at the teeth position in omega. I mean, it's kind of almost like kind of an identity. It's a projection onto a coordinate, right? It's a projection onto some coordinate. So I'm going to usually use xt to denote the projections, but you can use any letter. I mean, it's just an example, and you can check. And so check this is an exercise. You can check that xt is measurable. What does it mean to be measurable? It just means that when you take xt to the -1 of any singleton. So what is X? X is going to be an element of G. Okay, it's an element of G. This is why we use X and not little g, because
It's not a group yet.
because it's not a group. It's just a space, right? It's just a measure space. Maybe it's a topological space, but it's definitely not a group. Okay, we use X because points in space are X. Okay, and I don't care what other people say. And so we pull back this singleton, right? And all we have to do is we have to check that this guy is inside the set F. Okay, so you have to somehow find a way of writing this as some kind of union or complements or intersections of these guys, right? Countably many. In fact, you could do it as a finite.
Union of cylinders ends up with.
No, you have to be careful. Cylinders, the way we define them, you have to always look at some omega all the way up to time n.
Yeah.
So here you would look all the way up to time t, and then you have to give all the other options. So you have to take infinitely many unions on the other options, and we're using the fact that G is countable. If G was not countable, we would have to be careful on how we define the cylinders, and we have to let you have a cylinder with finitely many places, but anywhere, not just up to time n. But since G is countable, I don't care about taking all the way up. I made a smaller set of some lesser parameters to worry about. You have to be very careful.
Every cylinder is not defined by a finite set. It's defined by a omega.
Yeah. Okay. So and the theorem. So this is this is basically Kolmogorov's extension theorem, but it has to do also with Kara-Teodori's theorem. So this is Kolmogorov extension theorem. Tells you that if you can define probability measures on the cylinders, then you'll be able to extend it in a consistent way. I mean, of course, without getting contradictions, then you'll be able to extend them to a measure on the whole product space. And basically, it tells you, so assume there exist probability measures on GNF. So F is always going to be our cylinder sigma algebra on GNF, and suppose PT is running from 0 to infinity. Okay. So I have a sequence of probability measures, PT, okay, such that they have to be consistent, of course. For any x1, x0, sorry, up to x t, side G. If I take t elements inside G, okay, I want the two probability measures to be consistent. So I can look at the event, right? All the omegas, I can look at all the omegas such that omega j is xj for all the j is less than or equal to t. Okay, this is an event. I mean, in fact, this is a cylinder, right? This is exactly the cylinder, right? If you take the first t, so this is c. I could put the x's here, right? I could put an x here, maybe. Think of x as being an infinite sequence, but the first t plus 1 guys are these, right? And then I have a t. Okay, so this is what this is. So I can ask for the probability of this element, okay? So I can ask for under t plus 1, I can ask for the probability of this guy. Okay, so I'm just going to write it shorthand this way. Okay, and what I'm assuming is that this is equal to this guy. Okay, so whenever I ask with the bigger measures, whenever I ask, did the first t coordinates, the first t plus 1 coordinates come out to be this, then the answer, or what is the probability that that happened, then the answer for all the guys are the same going up. Okay? Okay. So if you have this kind of consistency, then there exists. And in fact, you could have these only defined for the extension theorem, you could have them defined only on the cylinders of size T. So it could be the situation, I can make it more general. I could say, okay, we only need to define the probability measures on all the cylinders that have at most T here. And all I need is a consistency going up. Okay. And yeah, so actually this I should write here T plus N for it. It should be consistent going up from T. And
The last one implies.
Yeah. Seems like.
well, we had kind of like the same T, so you have to be careful. But yeah, if you sum over all possibilities, yeah. But okay, I wanted to stress the consistency doesn't have to be on T. You start from some T and you take consistency upward, and then you can think of this defined only on the cylinders of size up to T. You can find the smaller sigma algebra here, where you can define these on growing sigma algebras, right? So there's a natural filtration, which we will always also use FT, which is this guy, right? So we know that this is a sigma algebra, right? And in fact, this is just spanned by the cylinders of size up to T. Size, I mean time up to T, right? So I don't want to do all the details because this is like measure theory, but if you define this, then you can have these only defined. So PT has to be only defined on FT. Don't care about what it does for other things. So you see the PTs are getting defined on bigger and bigger spaces in a consistent way. If you restrict the larger P to a smaller P, to the smaller filtration, then you still get the same thing. If you have that, so the Kolmogorov tells you, if you have the consistency condition, right, then there exists a unique probability measure P, okay, on the correct space, such that P of any cylinder, here I can write omega, okay, will be equal to PT of the same cylinder. Okay? So if you have a T here, you can put a PT here. You don't go lower than T. You have to be careful, especially if you didn't define them. Right? But you see, this means all of them will say the same thing, right? So it's impossible to have this condition if I don't have consistency, right? And consistency is already a sufficient condition. It's a kind of a technical theory. Okay. Let me give an example. Examples are more illuminating. Primitive example. First primitive example is IID. What is IID? This means I take PT of. So I only have finitely many omega, which are okay. So PT of let me write what the cylinder is. If I define it on all the cylinders, that's enough. Okay, then I'll tell you what they're about. So PT is going to be, what is it? It's I want to generate these, right? What is it what I'm saying? What is the probability that I get a sequence whose omega 0 is the omega 0, and the second one is omega 1, and the next one is omega 2, and so on, right? So what is it? Well, this is going to be the product, okay? J goes from 0 to T of mu of omega J, and mu is some probability measure on G. So remember, a probability measure on G, I can write as a, okay, so when we have probability measures on a discrete space, I'm going to cheat a bit. I'm not going to write them as probability measures as functions of subsets, because when we have a countable set, we always take the full sigma algebra. So a probability measure is just a vector of non-negative numbers that sum up to one. That's all it is. And we're just going to write it this way sometimes. So if I was very strict, if you were an introduction to probability, I wouldn't let you write it this way. I would tell you to write it, mu of the singleton of omega j, right? You have to write it like that. But I'm not going to be strict here. We all understand what a probability measure is. You cannot do this for these guys, because these guys are living in a big space. That's not the full sigma algebra. You have to be careful. Singletons don't define they don't uniquely define the probability measure. In fact, singletons will have probability 0. Okay, usually. Okay, so here, this, and if you use Kolmogorov, what you get, right? So you get these are consistent. You can see that these are consistent. It's actually easy to see, right? And what you get from Kolmogorov is you get IID. Okay, so you get IID. This is going to be the P. Because if you take any sequence, and you take any finite time, the probability that you see that those guys is just going to be the product of the news. So everything is independent, the same distribution. Okay. I don't remember where it was. Okay, so we have this, but here is a more interesting example. So we'll erase this more interesting example. So you see, this is kind of the maximal independence you can imagine, right? The maximal independence you can imagine, most primitive structure you can imagine. But let's give another example, which is more complicated. Okay, so fix another example. Fix some new probability measure on G. Okay. And for every x in G, let Px be a probability measure on G. So you give me an element, I give you a probability measure on G, not on G to the n. So it tells you, what are we thinking about? If you're at X, at next time I'm going to randomly select some guy, but it depends on the specific X. The randomness of who the next guy is depends on where I am right now. If you're at X, you'll randomly go to one of these. If you're at X prime, you'll randomly go to some maybe other distribution on G, okay? So you have some starting distribution, which is new, and some jump distribution, which is Px, depending on X. And then we can define Pt. Sorry for using too many P's. We can define Pt of a cylinder set, omega t. We can just define it to be, all I need is that they are consistent. Well, what am I going to do? I want Pt is going to say the following. What is the probability that I've seen, right? What is this event? This is the event that I see omega 0, omega 1, omega 2, omega up to omega t. Then I don't care what I see, right? But what is that probability? Well, I have to start according to nu. So the probability is first nu of omega 0, right? And then I have to jump from omega 0 to omega 1. So I have to do P omega 0 of omega 1, right? Again, probability measures on the group, I can, on the set, I can write as vectors, right? So I'm just not writing the little squiggly brackets. And then I multiply this, I have to go from omega 1 to omega 2. And product, all the way up to, I go from omega t minus 1 to omega t, and then I'm done, right? Because I don't care about anything else. I mean, I have to give the same number to this set, and it only has to depend on the first t plus 1 coordinates, okay? So I can define this, and you can easily see it's consistent, right? Because if I make this guy bigger, right, then summing over all the options will just give me ones in the product, and I'll get this, right? So you can check that this is consistent exercise, but it's not a difficult exercise. It's just law of total probability. It's just effective. If I sum over a coordinate here, it sums up to 1, right? Sum over all omega t's here, sums up to 1. and the disjoint union here of all the omega t's, right? It will give me the omega with t minus 1. So check consistency. Then what do we get from Kolmogorov? So Kolmogorov guarantees a probability measure, right? Which we will call P. Now, what does this probability measure depend on? It depends on these guys, right? Depends on these guys and on nu. Okay? So we will write the nu and not the dependence on P, on the P's. Why? Well, I don't know. That's accepted standard notation. Okay? But you should remember that this actually depends on P. So maybe I'm going to write it. This is actually a probability measure which also depends on the full sequence of these P's. And okay, and these actually depend on the full sequence of the PX's. So we can write it. And so you need all of this data. All of this data is required in order to decide who this measure is. But once I give you this data, I give you all of these numbers, right? This is just a list of many, countably many numbers, right? That's all it is. If I give you the list of all of these countably many numbers, then you get a unique probability measure. And this is going to be a Markov chain. We're going to use this to define a Markov chain. Okay. So, so first of all, some notation. Yeah, so notation, usually, I mean, I wrote it this way, Px, just to make you see who is the probability measure and who is the parameter, right? If you know you're at X, you have a probability measure telling you where you go next, right? So it's different who the probability measure is and who the parameter is. The X is the parameter, the input to the P. So when I sum over this guy, that gives me 1, right? If I'm going to sum over this coordinate here, I can also sum over that coordinate. It's a list of numbers for a fixed omega t that will not give me 1 necessarily. That's just summing over different probability measures at the same point. It could be anything. Okay. So usually we write Pxy or Px of y. You should think of this as a matrix. And this matrix, for example, if G is finite, this is an honest to goodness matrix. It just has entries indexed by G, right? If G is infinite, countable, so it's a countable dimensional matrix, okay? It's not such a leap of understanding to go from finite to countable, right? It's a pity in your podcast you don't talk about countable. I'm joking. I'm joking. I can't imagine what would happen. Although it's really the same thing. You should not, the red line between infinite should not go between finite and infinite. That is not, Lebesgue already understood this. The red line goes between countable and uncountable. That's where you start getting problems. Okay? Infinite and infinite, not really a big leap of understanding. Okay? So you should think of this guy as, you should think of this as matrices. Infinite dimensional matrices. We'll think of functions on G as infinite dimensional vectors, and I might say vectors instead of, they are vectors in a vector space, of course. I might say vectors instead of functions. Vectors and functions is the same thing. The same thing. Okay. We usually use this notation. All I want you to remember is that these are stochastic matrices. So you might see this word thrown around sometimes. Stochastic matrices. What does a stochastic matrix mean? It just means that every row is a probability distribution. So every row is just a sequence of non-negative numbers that sum up to 1. So it just means that Pxy are always non-negative. And if I sum over the y's, I get 1 for every x. That's all it means. That's all you need to think about. And you see that, okay, so, but summing over x is a completely different creature. You have to be careful. Completely different creature. I didn't say anything about symmetry here. I didn't say these matrices are not necessarily symmetric. I mean, in the general case. So you have to be careful. Okay, we will, of course, introduce lots and lots of structure. At the end of the day, we are going to work with matrices which are actually defined just by one vector. They're circulant matrices in the in terminology of linear algebra. Circulant matrices take one row and you kind of permute all the entries in the row around. Right? So if you have a finite dimensional thing, then it's very easy to understand what the permutations are. But if for an infinite dimensional object, you kind of have to understand what the permutations, what does it mean to permute? But we'll see. Okay. And these are square matrices, of course. These are square matrices in the sense that the index set for the rows and columns is the same set, G. Okay. So we have the stochastic matrices. So you see, if I give you a stochastic matrix and some maybe starting probability distribution, could be a delta function or something like that. So the pair of a stochastic matrix and nu, they uniquely define a measure, which we will call the Markov chain. And I will actually use the same name. Markov chain will also say P will also mean the probability measure on the product space. It will mean the same. I mean, I'll be a bit careless about specifying exactly who I'm talking about. So definition, we'll do it once properly. Let G be a countable set. Now you can define Markov chains on non-countable sets, and you can define them even in uncountable time. We're doing discrete time. Notice that whenever I write the little t's, I always said they were in n, right? They're natural numbers. So you can do it in continuous time and continuous space, in the sense that the space and time will be uncountable, and time will maybe be a real number. We're not going to. We're always going to work in the countable setting. It captures, in fact, all the good ideas, and in this case, it's even simpler in many things. Just to define, for example, Brownian motion, which would be a random walk even on R as a counterpart to random walk on Z, it would be terrible. Today or soon, I'm going to have a definition of what a random walk on Z is, and the random walk on R, continuous space, continuous time. I need half a course, maybe more, to define even what that object is. What's the probability says? What are the measures? So let G be a countable set. Let P be a stochastic matrix. And let nu be a probability measure on G, of course. And this is also on G. So stochastic matrix on G is indexed by, is a G by G matrix, non-negative numbers that each row sums up to 1. And the probability measure is a probability measure. Like we said, it's just a non-negative vector with who sums up to 1. And by Kolmogorov, this defines a unique probability measure P nu. So the reason we don't write this P is because this is going to stay, and we're going to play around with the little nus. We're going to play around with the starting distributions. Okay? On the space, the product space. So F is a cylinder sigma algebra in G to the N, right? Defines a unique probability measure. And we can also look at okay, so yeah. And this probability space is the space that we're going to be working with. And to be strict, and we can also consider the process, the G valued process. It just means a sequence of random variables, right? Given by xt of omega is omega t. So this is a sequence of G valued random variables, okay? Each one just looks at the different coordinate. And we say that xt is Markov P and nu. So all the data you need for a Markov chain is to tell me how the transitions go. That's P. He tells you how the transitions go. And nu tells you how to start. Okay, nu tells you how to start, and P tells you how to transition. And that's it, that's all you need. Okay? Now I want, okay, so what do these numbers represent? I really want to write this down. So, but this is the definition. So this is what a Markov chain. So and sometimes I'm also going to say xt, I'm going to write the sequence xt is a Markov chain with transition matrix P. Or I'm just going to say P is a Markov chain and xt is the corresponding sequence or something like that. I can even say the stochastic matrix is a Markov chain. Because you see, I can change this guy, still have the same P, and I can play around with all the probability measures here. Okay? These just govern what happens to x0. Right? Because of the way we define this P nu using this data. Okay? So so what does these numbers represent? So Pxy, I want you, okay, exercise. What is Pxy? Pxy is one of the list of numbers that we have. We have a long list of numbers, right? So Pxy is going to be exactly the probability, okay, starting from nu, for any nu, that xt plus 1 is equal to y, conditioned on xt is equal to x. Conditional probability, these are events of positive probability, you can check.
See that in your year's course, we started with this definition or something like that.
So
then
you
we
can
want to
define what the Markov
You
property
can
is.
start that way. I just want to say this probability space exists. Okay, then we can use it as definition and we'll see the Markov property in a minute. It's a different way of oops. Okay. Course equivalent. Okay. So this is the probability set. Now you can say that this, you can show that this identity is true for any nu and p. Well, you have to be careful that this guy has a positive probability. Okay, so this is true as long as you could concoct things where this has zero probability, and then you have a problem. We're gonna throw that under the carpet. I mean, we're gonna get rid of this problem once and for all in a minute. But so, what does this probability represent? What does this pair of, what does this matrix entry represent? It represents the probability to go from x to y. I don't care how you started. I don't care. You can just show that they're all the same number. Just you have to use the definitions of how we define the cylinder sets. Show that they're all the same number. Okay, and it shows you, and in fact, this is the basics of the proof of the Markov property, which we'll define in a minute. No matter what you start, how you started, if you know that you're at x at time t, the probability to be at time t plus 1 and y is just pxy. So these are the transition, and these are called transition probabilities. Right? Okay, so these are called transition probabilities. And by the way, what is nu? What is nu of x? Just if we're already here. I mean, so nu of x is just the probability under nu that x0 is x. That's what it is. Same thing. So if you know this probability measure, p nu, you can extract nu and you can extract p. Right? And the opposite, if you have nu and p, they uniquely define a probability measure. So you see that these two ways are just complementary ways, dual ways of viewing the same things.
And you want to say that this is the same for any t? Because
This is the same for any t. No, this is 0.
no, I mean
I said this is for any nu p and t. Yes.
yeah.
You can extract under the assumption that in the p nu of xt equals x is positive. Like if it's irreducible, if it's
No, so you have to have this.
No, just giving this probability, I cannot surely get all the transition probability.
Yeah, okay. I'm saying if you know the measure P nu,
Yeah.
then yeah, okay, you know the connected component. Yeah, okay. I'm not going to go into it. We're going to assume that they're all connected. I'm going to make that precise in a minute. Okay, so now let's do the Markov property. What is the Markov? So you can already see that kind of how can the Markov property not hold? You see, what we said here in this exercise is that if you know the numbers of how to transition from X to Y and the starting distribution, right? Then you know everything. Right? And you can write a computer program, it will sample how your guy is walking around the space. Right? So it's impossible that these things, it's impossible that anything that happened. So suppose, I wrote a computer program using this data and I pressed enter and it starts running. And then you come into the room after it did 100 steps and you look at the picture and you say, oh, at 100 steps, it's at position X. And you ask yourself, what is the probability that in the, at the next time it'll be a position Y, right? Well, of course, it's pxy, right? This is what the exercise says. It doesn't matter how I got to X. So even if I condition on more information from the past, somehow that doesn't bother me, right? So that exactly is the content of the Markov property. Now, I want you to notice this is an assumption on the process. It's an assumption on the process. Because if you didn't assume this, you could think of processes where the past does influence the future. But kind of in physics, if you will, we don't want to assume anything like that. Time plays a special role in physics, at least before you get into complicated space-time things, right? Time plays a special role in physics, and it plays a role that, you say you have a system, if it's at this state, it might go with probability, 1/2 to a different state, it might go with probability 1/4 to a third state, and so it has some probabilities written here on how it evolves, right? And then you have these new states, and then maybe this state goes here with a certain probability, maybe it can come back with a certain probability. So basically, you write down all your states and you put down all your arrows, and all the outgoing arrows sum to 1, because it's a probability distribution. Maybe there's only one that has a weight 1 on it, but that's going to describe your whole transition matrix. And in physics, you don't care how you got to a certain system. If you know all of the information, if you know all the relevant variables in the system, right, then you know what the next position is. Sometimes all the relevant variables is not what you would first guess. For example, in classical mechanics, right, if you have a system evolving, position is not the only thing you need to know. You also need to know momentum. So that's why you draw in, write in all the diagrams in physics. I never did a physics course, but if you take physics course, from what I understand, you see a diagram with P and Q, which is right. P is momentum and Q is position or something the opposite. Yeah. Well, so but you all understand, right? You draw these diagrams with position and momentum. Why do you do position and momentum? Because those are the relevant variables. Once you know exactly position and momentum, that tells you the full state of the system, in the sense that it will be a Markov chain. If you know everything about position and momentum, you know exactly what's going to happen next. Okay? And usually in classical mechanics, actually time is continuous, even if space is discrete, but time is continuous. So it makes things a bit more complicated. In fact, making time continuous is not so difficult from this. You can read about it in some books. It's not going to be for relevant to us, but it's easier to work with discrete time. But making time continuous is not the problem. Space continuous is making the space uncountable is maybe more of a difficult. Okay, so this is what we want to do, and the Markov property is the following. So let's write it down very, very carefully. So this is kind of an exercise. I mean, yeah. Well, okay, let's leave it as an exercise. Okay, so just a reminder. If I write this, if I write the probability of so if I write the probability of an event conditioned on a sigma algebra, maybe something like that, then what I actually mean is the expectation of the indicator, conditional expectation. Okay? That's a random variable. Okay? That's what I'm gonna write something like that down in a minute. And you have to parse it like that. But all it means is that you know all the information in this sigma algebra, and you still want to understand what is the conditional probability of that event given that information, which is a random variable, right? I mean, you sample everything in that sigma algebra, you sample the information, and conditioned on that information, you ask what's the new conditional probability of my event. Okay, so Markov property. Exercise. So I'll let P be a stochastic matrix or a Markov chain. We said, okay, we said Markov chain is also could be a stochastic matrix. Okay? So P be a Markov chain on D. Okay, I'm going to write it like this. I'll be too strict with the notation and the separation of things. Right? Now, in order to get a sequence, all you need to do is tell me the starting distribution. Okay, that's all. Right? So you need to do, and so the probability, then probability that xt plus 1 is y, okay, conditioned on this probability nu. This is for every nu, for every probability measure nu, okay? Probability nu, xt plus 1 is y, conditioned on. You see, now I don't need to worry about measure 0 and things like that. I'm conditioning on a sigma algebra. It's just some conditional expectation, right? Okay? Probability that at time t plus 1, I'm at y, given all the information at time t, or everything the process did up to time t. I should have stressed that when I'm writing ft, I always mean the sigma algebra generated by this canonical process x. Okay, up to time. That's what I mean. The natural filtration with respect to x. Okay. This is going to be almost surely, remember this is a random variable, it's almost surely the same thing as just asking for the conditional probability of xt plus 1 equal y conditioned on just xt. Now I'm conditioning on a random thing. Remember, what does it mean to condition on a random thing? Condition on the sigma algebra generated by this thing, which was just generated by all the pullbacks of the singletons with this function. Right, so the minimal sigma algebra that contains the information xt is equal to little x for all the little x's. Okay. Right, and what does this is also equal to almost surely? It's also almost surely equal to, I have to write a random variable now. I'm going to write a weird random variable. It's p of xt y. What is this? I claim that this is a random variable. This is a real valued, non-negative random variable. Why? You give me the random xt, right? So this is a function from omega to g, and then when you compose it with a function that takes an element in g and gives you the number p, that element y. So the composition of functions gives you an real valued random variable, which was what has to happen in a conditional expectation, right? So everything here is okay. Okay, remember everything in this part, right, has to be something real valued. So when we write a p here, we mean indicator of this thing that's a real value. Okay. The conditional distribution, no matter if this is the most information I can give you, right? And here it's kind of the least information I can give you, like just where you are. And it doesn't matter. You just have to know where you are, and you know the probabilities of how to go to the next stage. And of course, from the way I described it from the beginning, I mean, it's kind of almost obvious. This is one of the hardest exercises to prove in the sense that you kind of feel that it's so obvious you don't need to prove it, right? But okay, you just have to formally justify that this thing, this random object, is a version of the conditional expectation of this indicator. Okay, that's all you have to verify. And what it means specifically, so let's see a consequence of this thing. Consequence. Take a break. So just as a consequence, I mean, Markov property is a very simple property. Today we're going to do the strong Markov property, which is not a simple property at all. That's a more complicated property. Okay, so as a consequence, what happens if we have an event which is measurable with respect to ft? Okay, what does this mean? This is an event that you can decide if it happens or not by just looking at the first t plus 1 coordinates of x, right? Right? For example, this event could be at time t, you're in the set, you're at position x. It could be the at time 3, you're at position z, and at time 5 at z prime, and at time and t is bigger than 3 and 5. Okay, so anything you can decide, did it happen or not? Just looking at x0 to xt, right? Then we can ask for the conditional probability on the new, any new, that xt plus 1 is y, and the event A happened, conditioned on ft. Right? Could ask for that. Okay? In fact, let's not do conditional probability. Just ask for this, and okay, let's do this. Okay, so what I can add, something happened in your history up to time t, and the time t you're at x, and the time t plus 1 you're at 1. Okay?
So the history doesn't matter.
Yeah, so that's what I'm trying to say. This is a consequence of what's written here. This is the strongest kind of way to write it in the sense that it just encapsulates everything. Okay? Specifically, if I take a ft measurable event, okay, an event from ft, and I write it this way, then what can I do? Well, this is the conditional expectation of what? I mean, it's the expectation of conditional expectation, right? So it's the expectation of conditional expectation of the indicator of one event, right? So indicator of an intersection, I can just write as a product of indicators, right? So xt plus 1 is y, 1, xt is x, 1, a, right? I can write it this way, and I can put here a conditional on ft and take expectation of everything, so it's the same object, right? I just rewrote it in a complicated language. Now, when you're used to conditional expectation, you find this very easy because you see, it's immediate to me. I want to separate things that happened up to time t from the future. Then I know exactly who I want to condition on, time t, and everything gets separated by the natural laws of conditional expectation that we already talked about. These things, this is measurable with respect to ft, right? Because it's the indicator of an event that's measurable with respect to ft. This is also measurable with respect to ft because it just looks at xt, right? This is not necessarily measurable with respect to ft. In fact, usually not, right? But then when these guys are measurable, I can pull them out as constants, right? We said that we can pull them out as constants. So what do we get? We get that this is equal to the expectation of, this is new expectation, and we should actually, this is the expectation with respect to the measure, p nu, right? Whenever I write e nu, it's expectation with respect to the, it's the integral with respect to p nu. And this is the symbol for conditional expectation. Shouldn't have written the nu here. Conditional expectation is just it's a projection, right? It's just an operation. Okay, and I pull them out of the conditional expectation, so they come out here, right? And then inside, I have conditional expectation of this guy conditioned on ft, which is the conditional probability, right? Conditional expectation of an indicator is conditional probability. So this is the conditional probability of xt plus 1 equals y conditioned on ft. But we know what this is equal to. This whole thing we said is equal to the number p xt y. Right? Now, this indicator, what does it tell me? It tells me that xt is equal to x. So I can put an x in this xt. Otherwise, it's 0. Okay? So this is equal to, I get a pxy here. Pxy is a constant that comes out of the expectation. So I get pxy times the expectation of a product of two indicators. That's just a probability of the intersection. I just get the probability nu xt is x and a. So what did we get? We get this equality. This is sometimes phrased as the Markov property. No matter what you did in your history, no matter what A is, any FT measurable event, if you ask, what is the probability that I go from X to Y between time t and t plus 1? And I did A, it's the same as if do A, get to X somehow, do whatever you need to do, and then just transition in an independent, this is an independent toss. What this means is that the move from X to Y is conditionally independent of what happened up to X. It does not mean that they're independent. So there's no, the xt plus 1 and xt are not independent at all. It's very important where you were at time t to decide where you are at time t plus 1. But it is true that they're conditionally independent. In the sense, if you condition on exactly the position you are at time t, then the next, the coins you have to use, the randomness you have to use is independent from anything that happened of how you got to time t. Okay, and if you really, the best way to think about this is just think about physical processes, like in the most classical way, right? If I know the configuration of the state space of everything that's going on at a certain moment in time, so the laws of nature just tell me what's going to happen next, even if they're random laws of nature. Okay, I don't need to know how it got to this state, right? I look at the world, I see where all the planets are, then I know where they're going to be in the next time step. I don't care how they got, did God make them like that a second ago, or, did he do it 14 billion years ago, or maybe before that? Okay. So, so we'll take a break until 11:20. Okay, so I want to give an example. I want to do some more examples of Markov chains that we'll look about, and I want to first define what a random walk is. Let's start first with the actual. So, some examples. We're going to do random walk first. We're going to start with random walk on Z. Okay? We do it on R. Okay? So assume that ut from 1 to infinity are IID. Random variables, Z value. Okay? It's just random integers. Okay? We can look at the process. We've already looked at this process, right? Which is just the sum of the first P guys, and then maybe x0 is equal to 0. Okay?
You want to assume expectation 0 and kind of stuff.
What?
The U.
At the moment, I'm not assuming anything. Maybe in fact, I just write xt. I just define. So I have sum x0, and I define xt to be the sum x0 plus the sum. Okay. Let's not talk about x0. Okay. Maybe x0 has distribution of some U distribution. Okay, when I write this, it means that this takes values in Z and has the distribution nu. Okay. So nu of a number is the probability x0. So I claim that this is a Markov chain. Claim xt is a Markov chain with transition matrix given by The transition matrix is given by just how you take a step. And here it was important, not just that they're independent, but they're IID, identically distributed, same distribution. Okay, so the transition matrix P of x, y, how do you go from an integer x to an integer y? You add a mu, you add a u, you add a u, okay? So this is going to be equal to the probability that if I add a u to x, I get a y. And all the u's are the same, they have the same distribution, so I can just write it's a probability that x plus u1 or ut, it doesn't really matter, I can put any t I want here, is equal to 1. Okay. So if I rearrange this, this is probability that ut is equal to y minus x. Okay, so you see, this probability is going to be the IID probability measure, right? This is the probability measure coming from on the product space of IID U's. And using this probability measure, I can tell you what is the probability that you transition. It's independent of time t. So you can use any you want because they all have the same distribution. If they had different distributions, it wouldn't fall under the definition of a Markov chain the way we define it, because we define Markov chain as a time-independent object. Okay, you could also do other definitions. We said it's the same transition matrix for all times. So to get one transition matrix, they had to be in the same distribution, and they had to be independent so that if you know something at a certain time, the future is just continuing from that position. And so you can check that this is actually a Markov chain. Okay, you can check that actually this works. Okay, that you have the Markov property and that it works. Okay. So, oh, I didn't give that as an exercise. Yeah, I should have written it down. That if you have the Markov property, then actually what you have is a Markov chain. The only random sequences that have the Markov property are Markov chains. So you should also, in fact, it's a much more simple exercise. I'll give it in a minute. Okay, so this is an example of Markov chain. And what does it look like? It's a random process. It starts from some x0, which has some distribution. So maybe it starts randomly at some point. But then what does it do? It looks at u1, right? So it adds a jump u1. So it jumps to here. This is x0 plus u. And then it has u2. Maybe u2 was negative, right? So it goes from x0 plus u1, which is x1. Right? It jumps. Maybe it goes here. This is x0 plus u1 plus u2. Right? And so you see, you keep adding these things and moving around. Maybe they're nearest neighbor, maybe they're not. There's no neighbors here, right? It's just a formal sum of independent random variables. Okay, so Markov chains are generating this idea that started with maybe Polya, or looking at things, sum of independent random variables, or maybe all sums of independent random variables were something people looked at this beginning of 20th century. Okay. But then people started saying, okay, maybe I can do something more intelligent. Okay, so Polya was already looking at random variables with values in the integers or in the integers to the d or something like that in the lattice. Okay, and but then people said, okay, but I can also do this in a much more general setting. Right, so all I need is a way to add, in a certain sense, right, new independent objects. So we're going to change the whole perspective. I'm going to change the whole perspective, and instead I'm going to tell you what a random walk in a group is. Okay, what a group is. Okay. So random walk on a group. Now let G be a group. And let mu be some probability measure on G. Okay, so we have some probability measure on G. This is going to be our step measure. It's going to measure of taking a random step. Okay, so if you want, in the previous example, we could have taken G to equal Z, the integers, and mu is just the probability measure governing the behavior of the different U's. Each U is distributed according to mu. So let's use some probability measure and consider UT 1 to infinity, always you always have a first step, don't have a zero step, right? 1 to infinity, IID mu. So these are already now, these don't take values in the numbers. These are already just in some abstract group, taking values, group elements in some abstract group. Okay? And you can take some also you can take some probability measure G, and you can let x0. Let me write it out explicitly. You can have x0 with long nu, right? Just some new random. And then you can define xt. We're going to define it to be. Okay, I'm telling you what xt is. It is the take x0 where you started, and then you go to x0 plus u1. What does plus mean? It means multiplying the group. Okay, and then you multiply u2. And you do this in the correct order because groups are not necessarily commutative. Okay, and you get this random position. So xt is a random position in a group, and you get the position by each time multiplying by an independent random group element sampled from a certain distribution mu.
You can write that beta G instead of X.
Yeah, but we won't because you got used to X of it. And anyway, G is playing a few roles. We call it G because it's a group, but it's also playing the role of a topological space and a measure space. So you can't start calling it. Little g is going to be so many other things have to be called G. There's a green function, and there are also functions when you do F, H, and G, and so that doesn't live in the same place as you have to as it's not at the right position in the alphabet. Okay, so yeah, but, so this is what's called a random walk on a group, and this would and this I would so it turns out fact means that I'm not proving it, but you can easily prove it. Xt is a Markov chain with transition probabilities or transition matrix. P, how do you go from X to Y? Well, you have to multiply X by something in the group to get you to Y, right? And that something has to be a random element with distribution mu. So this is exactly the distribution mu at which element, if you multiply X on the right, gives you Y, the element X minus 1Y, right? So you have to be careful. You use what you know about group multiplication. Okay? This is the transition matrix. Now you see, this is what I said before, that the matrix is actually not going to be doubly parametered. It only looks at mu. I only need the distribution mu to get all the data, because this matrix is kind of a circular matrix in a certain way. Each row looks like some permutation of the group, of the way mu sees the group. So the row corresponding to X equals the identity element is just exactly how you would write down mu. But then a different row, you kind of shift all the elements by multiplying them on the left. And so all the rows are just some permutation of the first row in this matrix. Okay, so this is a very special structure. So this is a Markov chain, and it has this. You can think of a random motion on a certain group, and given that you're at a certain position, no matter how you got there, you have the Markov property, right? So no matter how you got there, the way you advance is by just multiplying on the right by a new randomly chosen element. There's some computer, you press a button, you get a random element, you multiply on the right, you get a new position. Press the button again, you get a random independent element. So the independence is in the steps, which is the U's, okay? And this is, okay? And it turns out that these things really capture some algebraic notions from the group. So they understand something about the actual group structure, even though they it seems like you can kind of get whatever you want. Well, in truth, you can get whatever you want if you if you really use weird measures, but we'll soon restrict the step measures that we take, and you'll see that they kind of capture understanding about the group. Okay. And this generalizes straightforward the fact that when you sum IID random variables, right? Even if you're in a lattice or something like that. I mean, so if this group was just ZD, and these were just generated random vectors in ZD, right? Then you would be summing these random vectors, right? So it would be some kind of random motion on a lattice. But of course, this is much more general. It could be random product of matrices, which is what Kesten and Furstenberg were looking at in the beginning, and there are many applications and examples of where these things are. In fact, there have been recent works on what's called complexity of black holes. Okay, I don't even know what those are, but it turns out I saw a few talks by Leonard Susskind and Scott Aronson has been working on these things. And at the end of the day, all they're doing inside they're doing random walks, or maybe not random walks, but walks on well, they are doing random walks in a certain sense on the group of unitary matrices over a certain even finite dimensional Hilbert space. Okay, so you take a unitary n by n matrices. It's a group, right? You take the product of two unitary matrices, you get a unitary matrix, and basically they're looking at random products of these things with independent increments. So they never called it that, and they were using lots of notions that basically kind of run, like in this theory, it's easy to understand. I don't know exactly. I mean, Scott Aronson definitely knows everything about walks. Okay, so let's a few more examples. Yeah, let's give one more example, and this is of a network, because this is an important example. Sometimes a group is a restricted structure, and a more general structure is a network. Okay, and this actually captures kind of the complete idea of what we want to look at. So I want to talk about networks. I mean, this is an important example to keep in mind, even though this is much more general than a group. Okay, so what is a network? So a network is a pair. I'm going to be less formal here because so it's a pair G and C. G is going to be a countable set. In fact, it would be better to write N, but N is a normal subgroup. G is a countable set. Okay, C is a conductance. What is a conductance? A conductance is a function from pairs of elements of G. Okay, to non-negative numbers. Okay. Sometimes you even let infinity, but let's forget it at the moment. Infinity would mean that you kind of attach two guys. So maybe you don't really want to use that. But you could put zero, definitely. Many of them would be zero. Zero conductance between two guys means you cannot make the transition. Okay, so it's a conductance. You can think of a pipe, and C is the width of the pipe. Okay, you want to push water through it and see, or push little electrons through it, and you don't fit.
And keyboard it?
Yeah. So it's a conductance. It's one over the resistance. No? Okay. So it's one over the resistance. Okay, just one over the resistance. That's all it is. Resistance is one over the conductance. That's a non-negative number. Okay, for each pair. We're going to denote not all of these pairs. Not all of these pairs are positive. We can denote by E of GC the set of pairs XY such that C of XY is positive. Okay, so those are the edges, if you want. That's what E means here. Okay, edges. Right? It's possible ways to go, but of course they have different weights. Okay, and what we restrict is two things. CXY has to equal to CYX. The width of the pipe doesn't matter if you look at it from each direction, right? Going from X to Y and Y to X. And the total mass, so C sub X which is the total mass coming out of X, or the total conductance coming out of X, not mass, but total conductance, okay, coming out of X. So you sum over all possible Y's and look at the conductance. This has to be a finite number. You're not allowing infinite conductance. And if you want to think about this, in a second, we'll turn these into a graph and degrees. If you put all the conductances equal to 1, then this is the degree. This is just an edge relation, okay? So if we have this, yeah, so a specific example of a network is a graph. In a graph, all conductances are 1, right? You just have pairs, which you say are edges. So all conductances are 1 or 0, right? You have pairs. For each pair, you say, are they an edge or are they not an edge? And you're only allowed to have finitely many edges at each guy. Could be different number. So Cx is the degree. And this is just the telling you, is there an edge or is there not an edge? Right? But of course, this is a more general thing. And a network is nothing more than a weighted graph. Okay? Nothing more than a weighted graph. Okay? But you can have infinitely many edges coming out of a vertex, but they have to have diminishing weights so that they're summable. That's all. Okay? And from a network, we can define a transition matrix if we have a network, and the transition matrix will be just
like that.
move proportionally to the size of, you have a bigger pipe, you want to go there, right? If you're pushing water, some of it goes here, some of it goes into the bigger one, right? So, and in fact, also electrons do the same thing. So P of xy is just going to be Cxy divided by Cx, right? So this sums up to 1. Okay, so the rows sum to 1. The columns, of course, if you sum the x's, don't tell you anything, right? So this is transition matrix. And so the Markov chain with this transition matrix is called, sometimes we call this the random walk on the network GC. Okay, so it's a random walk on the network GC. And there's lots and lots of theory. I have a whole chapter in my book about what you can do with these things. This is very important. This is in fact the theory of what's called reversible Markov chains. This thing is telling you something is reversible. Okay, time is reversible in a sense, to make, of course, precise sense of what that means. But these are special Markov chains, not they're restricted enough to give you a very, very, very rich theory. Not every Markov chain is like that, but these are. Okay. Another example, and of course, every random walk on a group is a random walk on a network. I just want to say that this is a generalization. If xt is a new random walk on G group, G, right? So if we have mu, right? What is a new random walk? Remember, it's multiplying by new independent elements, right? From where you are. Then you should notice that we can define C by Cxy is equal to mu x minus 1y, which is incidentally Pxy, right? In this case, it's the transition matrix, right? And what you should notice is that no, that's not what I wanted to do. That's not what I wanted to do. Sorry.
Want P of xy to be and then
No. Sorry. So if x is a mu random walk, and if mu is symmetric, okay, then I can define this conductance, and you see that it is symmetric, and that this and GC will be a network. And the random walk on GC is the mu random walk. the same process.
Something is and over there we define P of X, Y,
Yes.
P of Y.
If I define that C and mu is symmetric, then Cx is going to be 1.
Yeah, but if we define P of X, Y like this, missing a constant, right? Or
No. Look,
maybe
for this situation, I had a P. This is P of mu.
P of mu.
This was the P I started with. Okay, I define a new conductance, and you can check that Cx is 1 for every x.
Yeah.
Okay, so it's going to be the same. The P coming from the network is going to be the same P coming from the new random. Okay, so at least for symmetric random walks, yeah, actually, I should have been careful. It is not true. It is not true. The non-symmetric measures mu here always give networks. Not every random walk is a network. Random walk on a group is a network. Every symmetric random walk on a group is a network. On Z, they are always networks, but that's different. It's a very special case. Okay. But if you take random walks, I mean, nearest neighbor on Z, okay, not going to go into. So let me just state. So these are the Markov chains we're going to want to work with, and I need some properties of Markov chains, okay, that we're always going to assume, and I want to translate the language for Markov chains into the language for random walk groups, okay, or networks. So definition. The Markov chain with transition matrix. Sometimes I'll just write a Markov chain P. You understand that I mean the process coming from this transition. This matrix P is irreducible. What does irreducible when people are thinking of Markov chains, what are they thinking of? They're thinking of the fact that you cannot split this Markov chain into two parts such that each one just has its own laws. So you have a Markov chain is your universe, your physics. Okay? And now you say, well, maybe I'm actually talking about, two different universes in the multiverse, right? So this one has these laws and this one has these laws, right? And they have nothing to do with it. They never communicate with each other. Okay, right? So you can think of two places in the universe which are separated by more than light can travel, right? So there's no way that they can communicate with each other ever, and so the laws here and the laws here could be different or the same, or but nothing here affects anything here, and so they're completely different. So then it's reducible in the sense that what you study this one, you study this one, right? You put physicists here, put physicists there, they do their experiments, they make theories, and nothing can affect one the other, so they're completely two different sets. And so they're not the fundamental objects we want to understand. In the sense, in ergodic theory, you would say there's a minimal object, right? So, I mean, you want to look like a minimal action, right? Why do you want to look at a minimal action? Well, if you have a non-minimal action, you separate it into its ergodic components, and right. So each component does its own thing. It doesn't know about it. Yeah. Okay. So so Markov chain is irreducible if you cannot split it into these components. What does this mean? It means that any guy can affect any other guy. That's what it means. From one place, you can get to another place. Okay? So what does it mean that you can get to another place? Well, it means that there is some probability, positive probability, that you can reach from any state, any other state. Okay? So Markov chain is irreducible if for every x and y in my state space, of course, okay, there exists some time t such that the probability that I can be at time t at y, and let's write it this way, conditioned on x0 being x. A different way to write this is the probability sub delta x, right? I could write sub delta x. Okay, so this is the same thing. So delta x, xt is y. What I want this to be is positive, strictly positive. Okay, so for any pair of states, there's one way to get from x to y. There is a way, there's some positive, maybe very small probability to get from x to y. Okay, if you're at x now, at some point in the future, you might be at y. Okay, it could never happen. It could be the case that if you run the process randomly, you never go through. Why? Because probabilities are diminishing, and and you go far away, and you never get close to one. But there still was a positive probability that you would have went to one. Maybe it doesn't happen, but it doesn't have to. It's not probability one, just positive probability. Okay. I want to give you an exercise. I want you to prove exercise. Show that P is irreducible. Of course, I mean a transition matrix of a Markov chain. If and only if for every x and y, there exists a t such that the tth power, matrix power, okay, multiply matrix t times with itself at the point xy. So this is a new matrix. I can now say, well, this is greater than 0. Okay. If you know anything about the word irreducible in matrix theory, right, then you know that this is the definition of an irreducible matrix. Sometimes in linear algebra, they define an irreducible matrix as a matrix such that for any two indices, there is a power for which the matrix will become a positive entry in that index, non-zero entry in that index. Depends if you're talking about only positive matrices or if negative values, but non-zero in that position. Okay, this comes from this idea. Okay, and then we don't have a problem when we do these irreducible things. Remember before when I was talking about the Markov property, I said, well, if we condition on xt being x and we start some distribution, we have to be careful that has a positive probability. Well, in a certain sense, this kind of gets rid of that difficulty. And for large enough, or for some t, we will be able to be at x. So we can condition on being at x at a certain time. Okay. Yeah. One more thing. What happens when it's a random walk? So another exercise. So let U be a probability measure on a group G, and consider P mu, right? What is this? This means that P xy is just mu of x minus 1y. So this is the transition matrix coming from the probability measure mu that we said before, the random walk matrix. So what is this random walk? Let's think about it for a second. What is this random walk irreducible? When can you get from every state to every state? It has to be that no matter where you are at a certain point in the group, you can get in maybe a sequence of multiplications, some elements that can move you from x to y. But it's enough to get from 1 to any other element, right? If you want to get from x to y, you need to do x minus 1y. So it's enough to get any element from 1. Okay? So, and this is called being adapted. So we have a probability measure on this, then show that P is irreducible if and only if mu is adaptive. What does adapted mean? I'm going to write down the definition. What is adapted? So the definition of adapted is mu is adapted. Sometimes this is called generating. Okay, so it could be generating. If this is definition, we just call mu adapted if it generates G as a semigroup. So if mu generates, sorry, mu doesn't generate anything as a measure, supportive mu, okay, generates G as a semigroup, which specifically means for any x and g, there exists S1 up to Sn in the support of mu. So let me even write what the support means. What does it mean for Sn1 up to Sn is for mu? All of them have to have positive mu measure, strictly positive mu measure. That means to be in support of mu. And the product of S1 up to Sn is X in that order. Okay, so this is what generating is. And we will only work with random walks like that, because if you have a random walk which does not generate your group, is not adapted, then well, you not looking really at your group. You're looking at a smaller group, which is generated by the support of mu. Mu has no idea. The random walk of the mu random walk has no idea that you're in the bigger group. You're just looking on a smaller. Okay. Of course, when mu is symmetric, then generating as a semigroup or generating as a group is the same thing, because you have the inverses for free. But if it's not symmetric, you have to be careful, because maybe you can walk in one direction, but you can't walk in the other direction, so you have to be careful. Okay, so this is definitions, and the next time we're going to do the strong Markov property. Strong Markov property tells us that not only can I condition on being at certain point x, just kind of restart from x, just say the whole future just looks like I started from x, but rather that if I condition on a stopping time, suppose that I have a stopping time. Remember, stopping time is something has to do with the process. I have a stopping time, and I say stop at that stopping time, and then run your Markov chain. It's the same thing as asking. So asking questions about what happens after a stopping time is the same thing as if you know that at a certain stopping time you were at x. It just you restart the Markov chain from x. It doesn't matter. It's independent of the past of how you got there. Now, that's not true for every time, but it is true for stopping times. Okay, so that's a strong Markov property, and that's a much more restricted property than the regular Markov property.